everyone, welcome to Triaright, the new era of learning. This is Pack 365. In Module 5, today we're going to discuss about reinforcement learning. The concept we discuss about some little examples, some little bit examples on reinforcement learning, okay, and defining the reinforcement learning problems, marquee decision process MDP, okay, and solving and RL problems, okay, dynamic programming, Monte Carlo methods, and temporal difference learning. Okay, let's come to the top. What is the reinforcement learning? Okay, so in simple terms, we call it as it is also known as the learning from trials and errors. So we can tell as what is reinforcement learning. With reinforcement learning is a learning paradigm where an agent learns from the sequence of decisions by interacting with an environment, unlike supervised learning, okay, where labeled data is provided. Uh, RL is a trial and errors using the rewards and the penalties, right? Using the rewards and the penalties. So in here we can say the most important key method, key element, the mathematical framework we use in MDP, we all discussed about it, Markov decision processing. Okay, let us take we have in that we have a set of possible states and set of possible actions and transition possibilities of P, and we have the reward functions and discount factors, short-term and long-term rewards we have in that. So it is a type of loop, we can say that. It runs when it starts, it enters into the loop of the reinforcement learning and up to until it get the proper maximum reward. Up to the loop will be continuous. Like a agent observes the current states, an agent selects an action, enrollment and returns its rewards, and next step it moves to the next step. Agent updates its knowledge, value function or policy. It's repeat until the movement of the rewards will be increased. Okay, in that we have core functions like policies, value functions, action value functions, where policy is that defines the behavior of the agent, probability of taking actions and instance of states, and value functions expect return starting from the states as policies and action value function that expect something written from the state and taking an action, then following the policies, right? We can say the type of reinforcement learning we has a model free versus model based. Like model free means no knowledge of enrollment diagnostics. Okay, example Q learning policy gradient. Okay, model based means learning the traditional and reward models using symbolizers of the simulations of planning. Right. So this is about the Q learning. Sorry, this is about the reinforcement learning. And instead of I show you some little bit of examples to understand the better understanding about the Q learning. So let us assume we have a reinforcement agent called dog and enrollment called a owner. Is a dog's owner. So instead of the dogs and the owner, where the dogs takes action to the move towards the environment, like owner, right? It makes some action while moving to the environment, right? The agent want to move forward to the environment. It makes some actions like jump or walk or run, right? Whenever the agent makes some actions to move towards the environment, the environment will return the feedback, returns the rewards, or instead of feedbacks, we can say we say rewards. It returns some reward to the agent. Like okay, so instead of this, we take another example to understand it better in a child way. So another example, we have an agent called baby. Okay, we have a task called we have milk and empty glass or no milk. Okay. Environment is nothing but our parents. Take a view. So if the baby did any mistake, the parent will definitely punish the baby, right? Instead of they beating, they punishing like how they did not provide any milk to the baby, did not feed any milk to the baby, right? I it is the punishment for the baby. Empty glass. Where the baby is good and calm and silent, it will get some rewards. It moving some actions with a good, calm, and silent. So the baby will definitely get the reward, right? Instead of you doing any good thing, you get the rewards. Like we can say that if you have in classroom also, if in an office also, with that we did, if the manager comes and give a task to you, if you did your task in perfect time and in time with a proper way, you get a reward of bonus, right? If you did the work in lags and late, and you get the punishment by the cuttings and anything, okay, load of works. Like the punishment will you get extra work. Like that, the environment also work like this, okay. So let us take in a little bit example in robotic way. So let us take if we have a robot in a room, right? A robot in a room. So actions what we prefer up, down, left, right, right? Up 80% for the 80% of move up and 10% move left, right? And 10% to move right. So you have rewards, reward plus one at the 4, 3, 4, 3. Here we can see the column 1, 2, 3, 4. Okay, we see the plus one at 4, 3, right? 4, 3, we had a plus one and minus one at 4, 2, right? Here we can say 1, 2, 3, like 1, 2, 3. Here 4 and here say 1, 2, 3, like that. So here we have a 4, 2 at the point of minus one and 4, 3 at the point of we have plus one. It is a reward. And reward is another reward is for each step, minus 0.04 for each step. Okay. So here, what's the strategy of the achieving max rewards and what is the action where deterministic? Okay, so let's see. Robotic the action where rewards, which is the starts. We have the action, we have the rewards. Now, what is the solution? Let's take the robotics moves the up towards the up and towards the right to reach the reward. So it makes the action. Only if action determines, not in the case of action or stochastic. Okay, our solution policy mapping for each state is an action, right? Let us see. Again, it's come from the left. Again, from the left three times and up two times and three times right. If it takes the left two times up to it, like that, is want to chase the reward. So step one, optimal policies. And now it is reward for each step, right? Reward for each step, like it moves from upwards to direct three step for reward and downwards to the three step right to the reward, like that it makes the efficient way to find the reward. Okay, and the reward for each step for 0 comma minus 1 it takes like that. Okay, for 0.04 it takes the easy way, like takes the here we can take two lefts, one up and one right. We take the reward after. Instead of that we can take three rights, two left, sorry, three lefts, two upwards, three rightwards, like that. So definitely making an action, right, for each and every step. So instead of that, we take another example like pole balancing, like TD government, Gary Filusiro, okay, and helicopter. So here we can say no teacher who would says good or bad. Is reward 10 good for or bad? Rewards could be delayed, similar to control the theory, more generation fuel constants, okay? And explore the environment and learn from the experience, not just blind. Such to try to smart about it, okay? So resource allocated in data centers like load balancer. Here we have application A, application B, application C. So hybrid line enforcement approach to the automatic resource allocation. Okay. So we can say Kishore, Kishoro, Jong, Das, and Binani, IBM, like that. Okay. So outliers. We discuss about the no examples. Now we come to the picture of Markov decision processing, like MDP, right? So what is nothing? MDP is nothing but we can see the set of states and set of actions repeated way. Okay, it transition the models, right? And we can see it has the reward functions and it has renew state and old state, right? And we can see the definition problem. To define the RL problems, like formally we use the concept of Markov decision process, right? In this, we can say an MDP is a framework used to describe an environment in the reinforcement learning it includes. Okay, so let's take states as S and let's because all possible solutions of agent can be in and action as A, like all possible choice of the agents can make and transition functions we call as P, the probability of moving from one state to another state given by the action, right? And we take final output as reward function has or and you immediately reward received after the transaction. You can say transition, like moving to another state, like discount factor gamma. How many futures rewards are valued? Okay. This is the property says in future state depends on the current state. Okay. And actions is not a past state. So we see here the goal maximum, right? Like the how its system can be works. Okay. So now let's come to another topic. Let's computing returns from the reward. All right. Here we have concepts called exits versus continuing task, game over after nth steps, right? The game at the end of the step, that definitely it wants to end, it wants to collect the rewards, right? Optimal policies depends on the end, harder than the analysis, okay? Active rewards and discount rewards. We have the discounted rewards like that. So value functions, in the value function, we have the state value function, which is the V expected returns when starting in S and following to the pi, okay? State action value, we have expected returns when the starting is S and the performing A and the actual following will pi. Use it for the finding the optimal policy. Can estimate from the experience, pick the best action using Q pi full of S comma A, right? So Bellman equation. An optimal users function. There is a set of optimal policies where V pi defines the partial ordering on the policies. They share the same optimal value functions, right? Here we Bellman optimal equation here also applies. The system of the non-linear equations solved for the V and S value of the functions. Easy to extract the optimals, having the Q of make an easy and simple. Even the simple, we use this method for we make the simple, okay? And from the outliers. Now we want to discuss the solving the RL problems called like dynamic DP problem. So the dynamic probleming is nothing but this main idea used for first we discuss about the some little bit about it. So the it requires a complete model of an environment, transition, probabilities, and rewards, right? Uses the Bellman equations to the iteratives, improves the value estimators, right? It algorithms like policy iterations, alternated between the evaluating and a policy and the improving it, right? And value iterations, right? Iterative updates, values, function to find the optimal policies. Okay. So uses the value function, it structures the search for a good policy, need a perfect model of the environment, right? It's two main components. We discussed about the policy evaluation and policy improvement, right? Compute with pi, v pi n from pi, and pi based on v pi, right? So starts with an attributary policy, repeat evolution improvement until the convergence. Okay. So we can see the policy here, both the difference about the policy evolution and the policy improvement. So in both, we use the Bellman equation, define the system of the equation to solve, but is use the iterative version, right? Start with an arbitrary value function and V0, iterate will until the K. Like the process will be defined, the property invented. So I used to check the mathematical calculations here. So I used to show here, we can use to understand the what the function behind the running, okay, what the action is running behind the enrollment, right? So we see the policy of iterations, policy of value iterations here also. The two nested iterations, too slow, do not need to converge to v by k, just move towards it, okay? Not a particular large unknown or unknown environment, because it is need to have the full model of the concept, right? And we say using DP. Need complete the model of the environment and the rewards robot in a room. We say the start space and action space and the transition space. Right, we can use DP to solve robot in a room or backgammon and helicopter like that. So instead of that, we completed we call another outlier here to state representation. So we can solve Monte Carlo method. About the Monte Carlo method, it is used to learn directly from the experience episodes or not from the model, right? Estimate the value functions by averaging the returns observed after episodes. Useful when the environment is unknown or too complex to model, right? Requires a complex episode. You must want to until the end of the episode to update like types every visit and first visit. Monte Carlo methods is used to the episodic episodic tasks like games or simulation. We use it. Okay, the steps of the first visit, and we have the mark. There's all strategy about it. Maintaining explorations here, maintaining exploration over the soft policy instant with probability of minus e performing like that. We have the value. We'll keep exploring the environment, cementation experience like we all know about the cards. about poker game, and we see the audio. We have the 56 cards about it, and we have 13. Each section we have the 13 cards. We can see the here what the function of the M we performs here, and we check the outlier of temporal difference here. So it is the combined idea of the DP and the Monte Carlo. So temporal difference is nothing but like an Monte Carlo can learn from the raw experience, right? And like DP, it updates the estimation based on the other learner estimations is not waiting for the full episodes, right? And the key algorithms is TD, it updates the based on the one step look upward, or we can say as a one step look ahead, right? Okay, in this we use the state action and the state action reward state action also. SARSA, SAR, SA updates using the action actually task. In this we use Q learning also updates the using the policies. So here we can see the programming neat models and update the step, right? And we can see here and with the difference between the MC and the TD. So we can say the distance what the behavior is actual. So it is nothing but SA or SARSA is nothing but we can say that SARSA is nothing but we said the reward system. It is also one kind of reward system. So we can similarly call I said that we can similarly called as it. Wait a second, my system is little bit hanging. Okay, now it's fine. I just connected one this. Now it's okay. Okay, so we know about SARSA. SARSA is nothing but it is a similar Q learning, but it is a key difference. Okay, so about the SARSA, we also discussed about the state action, reward state action. Like, okay, it is a model free on policy reinforcement learning to algorithm used to learn a policy that tells the agent what action to take under the circumstances. Okay, so in depth, SARSA is a state action, reward state action is and similar to the Q learning, but with a key difference in how the action for the next state. Okay, it's selected and used the updates. While Q learning uses the best policy action in the next state, updates the Q value of policy. The SARSA uses the action actual taken. Okay, actual taken the actions to the current policy. It is works on the on policy systems. Okay. It has the current state. It starts with the random policy, update queue, and after the pi, after each step, again need the soft policy like current state, current action, reward received after the taking action, next state, next action, like that. It moves. It repeats the initial states. Okay. And now about the Q learning. So, what is Q learning? We all know about the most, it is a popular method. So, Q learning is nothing but it is one of the most popular and the foundational model free, right? Reinforcement learning algorithm. It helps to agents to learn the optimal actions, selections, policies for any given environment without the needing of a model of an environment. Like, it's okay, let's break into steps. So Q-learning is a value-based. It is the off-policy algorithm that learns the quality of the Q value of an action, which represents how the good and an action is in a particular state. It checks okay the Q value of the state action pairs, like we can say SA or A, or AS. Like that, we can denote it as a variable of Q of SA, comma, and here we still can show we can say that we have the Q and instead of STAT like that. Expected the future reward for the taking the action in states. Okay, and the overtime of the queue learning updates the its estimates of the queue of FA based on the rewards and received. Okay. So instead of the steps, we are installing the queue table, and after a table will dimensional state of X into actions, initializing filled with zeros, right? The loop will be run so with the current state, right? If whenever the loop will be run and it kind of complete of the iteration, wherever the iteration passed or it move or it jump, it moves forward, the iteration will get one. After that, it reach another iteration. When iteration 2 of the completion of iteration 1, which is to complete the end state after the 1 become 2. Like that, it moving the climbing the rewards. Okay. Choose an action, take an action, observe the actions, rewards, and the next step, updated Q values, like that. Okay. So repeat until the coverage of numbers. Okay. So this is nothing but about the true learning. We have discussed about there's some way, some little bit about the little bit information about what the reinforcement of state representation, problem balancing, like that, moving a car left, try to keep the pole balanced, right? Step representation. So position and velocity of a car and angle and angular of velocity of the pole. What about the market properties? We need more info. So it needs noise in sensor, temperature, binding, like that. So it is a function approximators. I guess you have to some little bit more detail in it. So the futures and the splitting and the aggregations here, splitting the state space, okay, and state aggregations. You can see here start with a single state and split a state with a different parts, right? The parts of the state for different values. When you start with a single and it is split into different parts, right? State agents nothing but you start with so many points and merge with the similar values. While the nearest values it can be split and it can be merged the values. Okay, we can see here designing the rewards robot in math and chess, good, bad, like that reward system we can calculate as that indicates what we want to accomplish and not how we want to accomplish it. Okay, about the case study of okay, the overall of summary about it. So reinforcement use it when need to make decisions in uncertain environment, right? Solution methods for dynamic programming need complete model. Monte Carlo is time different learning of Sarsa and Q learning, and most work algorithm sample need to design future states and representations. Okay, so this is about the all about the Q reinforcement learning. So I hope you guys you understood well. Thank you.